All right, so here are the things that you need to know, the words that you need to know, and how many sides they go with. So the first one is a triangle. Triangle has 3 sides. The second one is a quadrilateral. Quadrilateral has 4 sides. I'm going to go through them kind of quick because you can always replay the video later. The next one is a pentagon, 5 sides. Hexagon, 6 sides. Heptagon, 7 sides. Octagon, 8 sides. Nonagon, 9 sides. Decagon, 10 sides. Dodecagon, 12 sides. Dodecagon, D-O-decagon.
What about 11?
I skipped that one. So anything else, I'm going to refer to it as a however many sides it has dash gon. Those are called n-gons if you want the variable representation. So an n-gon can be any polygon. An 11-gon would be an 11-sided figure. A 17-gon would be a 17-sided figure. All right, so what we're going to do is we're going to take a look at, I've got some polygons sketched out here. These polygons are convex, which means that all the angles inside are less than 180 degrees. You don't have any interior angle that's greater than 180, or you can, every diagonal you can draw remains inside the polygon itself. So if I were to go ahead and take and break up, well, let me do something first. Let's take a look at a 4-sided figure that's a rectangle, also known as a quadrilateral. If I tell you that this is a rectangle, what do you know about all the angles inside? They're all 90 degrees. So a rectangle is a 4-sided figure in which all of its interior angles are 90 degrees. What would the interior angle sum be? So 90 plus 90 plus 90 plus 90 is 180? 360. So in a 4-sided figure, you might be surprised to know that in every 4-sided figure, every quadrilateral, not just the rectangle, the sum of its interior angles is always going to be 360. Let me show you why this is. The thing that I love about triangles, and we really spent a lot of time on triangles. In fact, everything we've done this 9 weeks has been about triangles. The thing that I love about triangles is that triangles are really the building block of all polygons. So if I connect the diagonals of this rectangle, I've really divided it into 2 triangles. What do you think the sum of the measures of angles 1, 2, and 3 would be in that upper triangle?
180.
180. And what do you think the sum of the measures of angle 4, 5, and 6 would be? 180. And so since this can be divided up into 2 triangles, and the sum of the angles inside the triangle is 180, lo and behold, the sum of the 4-sided figure is 360, because it's 2 triangles, and 2 times 180 is 360. Now, what's cool is not only is a triangle the building block of a 4-sided figure, but a triangle is the building block of any polygon. Because you can take any polygon and you can divide it up into a series of triangles. So the pentagon divides up into how many triangles? The hexagon divides up into how many triangles? 1, 2, 3. I'm going to go with 4. The septagon, I called it a septagon. That's not the English version of that. The heptagon, how many triangles? 1, 2, 3, 4, 5. So if I were just to do a little bit of pattern recognition here, sides, triangles. For 3 sides, we have a triangle. That's one triangle. A 4-sided figure had 2 triangles. From looking at our pictures, 5 sides, 3 triangles, 6 sides, 4 triangles, 7 sides, 5 triangles. If I were to project how many triangles would exist in a 100-sided figure, what do you think I'd come up with? Based on this pattern, 3 goes to 1, 4 goes to 2, 5 goes to 3, 6 goes to 4, 7 goes to 5, 100 would go to 98. Why 98? Right. All of these numbers of triangles are 2 less than the numbers of sides. So a 10-sided figure would have how many interior triangles? 8. And remember, inside the triangle, we have 180 degrees as the sum of its interior. So if I know how many triangles are inside, I can determine by multiplying that number by 180 how many degrees are inside. So that would be 3 times 8 is 24, carry the 2. That would be 540 degrees for a pentagon. All this is going to lead us to this formula right here. The polygon angle sum theorem, great note card, which says, and I think this formula is even on your sheet, the interior angle sum of an n-gon, however many sides, is the number of sides minus 2, that's how many triangles, times 180. So the n minus 2 comes from the fact that based on our pattern recognition, that's how many triangles would be inside it. What I like to refer to this is the IAS, interior angle sum. And the IAS is equal to n minus 2. Figure out what that is first, and then multiply it by 180, where n is the number of sides of your figure. So, if I wanted to work this problem right here, what is the sum of the interior angle measures of a heptagon? Well, a heptagon has 7 sides, like I've said earlier. So 7 would be what n is. So that's 7 minus 2 times 180, which is 5 times 180. And if you do the math, calculator in your head, whatever, you should get 900. So the interior angle sum, or the IAS, for a 7-sided figure, a heptagon, no matter how I draw it, its angles are always going to sum up to be 900 degrees. Does that make sense? Does anybody have any questions about what I've covered so far?
What did you say? IAS?
Interior angle sum. I just don't like writing out the sum of the measures of the interior angles. So I made up something that represents that. All right, here's what I want you to do. I am going to reveal to you a set of problems. And I want you to use the IAS formula to solve part A and part B. Part A is, what would the sum of the interior angles of a 17-gon be? Part B is, hey, the interior angle sum is 1980. What's the measure, or how many sides did it have? So you got 2 different questions to do here. And after you finish the question, you can check with your partner. All right, let's see how you did. For part A, I used the IAS is equal to n minus 2 times 180. What's n in this case for a 17-gon? Yeah, that was pretty easy to determine. And so 17 minus 2 is 15. And 15 times 180, 2,700. Everybody okay with that one? Sweet. Now, part B, I'm going to use the exact same formula. So the geometry is knowing the setup here. Do me a favor and shut that door. So the setup is going to be exactly the same. The only difference here is, what is it that I'm plugging in? Well, I'm looking for the n. I'm looking for how many sides are in the polygon, but I know the interior angle sum. So now 1980 is going to go here, and I then have an algebraic equation I can solve. Not too complicated. I distribute, so that's 180n minus 360. I add the 360 to both sides, and that gives me 2340. And then I divide by 180, and that gives me 13. All pretty easy when you have calculators available. So part A, plug everything into the formula, leads you to 2700. Part B, we've got the 1980, and it leads me to find n, the number of sides. Yes?
Can you report B, can you divide by 180 and add 2?
Yes, because if I divide by 180... All right, so when we talked about triangles, if you had a triangle that was equilateral, or all its sides were the same, that triangle was also equiangular. Surprisingly, that facet only shows up in triangles. For example, you can have something that's a square, and that's a four-sided figure that's both equiangular and equilateral, but a rectangle is only equiangular, and a rhombus is only equilateral. So there are figures that exist that are four-sided that are not both at the same time. And here's an illustration of a hexagon. So here we have an equilateral polygon. All of its sides are equal. The same amount of sided figure has all of its angles equal, but these are not both equiangular and equilateral at the same time. When we do have a figure that's both equilateral and equiangular at the same time, we call it a regular figure, a regular polygon. So if I have a regular hexagon, my claim is that all the angles are the same and all the sides are the same. And we will be using the term regular a lot because there are certain properties that happen with regular figures that don't happen with other figures. So an equilateral triangle is a regular triangle. A square is a regular quadrilateral. Everything else after that is regular whatever it is. So in a regular figure, you can find the measure of each interior angle just by knowing that it's a regular figure and knowing how many sides, you automatically know its measures. Just like in an equilateral triangle or in a regular triangle, we know all the angles are 60 degrees. And in a square, we know all the angles are 90 degrees. If I have a regular pentagon, so a regular pentagon is going to be where n is equal to 5. So if I know that n is equal to 5, then I know that the interior angle sum is equal to 5 minus 2 times 180, or 540. But I also know how many sides it has, and if I take that 540 and I know that all the angles are the same and divide it by 5, then I can get that each angle is equal to the sum of its interior angles divided by how many angles there are. So 540 divided by 5 leaves me with 108. So inside a pentagon, if it's regular, I automatically know that each angle is 108. Let me kind of graphically display that for you. So a regular pentagon is probably going to look something like this. That looks regular-ish. And then a non-regular pentagon could look like this. So here, if this is regular, that means all the angles are x. Or x plus x plus x plus x plus x is equal to 540. But here, if all the angles are not the same, then this would be A, B, C, D, E, and A plus B plus C plus D plus E would equal 540. Well, in this equation, we just have one variable to solve for, and we can say that x is equal to 108. But in this equation, we've got 5 variables. I would need 5 equations to solve for 5 variables, 5 different equations. So if you have a regular figure, you can determine the angle measure of each interior angle. If you don't have a regular figure, you can't. So it's important to be able to first identify what a regular figure is. Then after you've identified that regular figure, you need to be able to add on any extra properties that might occur because it's regular. So here's an example. We've got the little housefly, and its little eyes are made up of about 4,000 hexagons. And the hexagons are regular hexagons. They all fit together perfectly. And so these hexagons, we could determine the interior measure of the angle inside the hexagon by using our formula for a hexagon. That's going to have n is equal to 6. So interior angles equal 6 minus 2 times 180 all over 6. So if I move that up to here, that's 4 times 180 divided by 6, which is 720 divided by 6, which is 120 degrees. Is everybody okay with that? So all of the interior angles of a regular hexagon, and it has to be regular, are 120 degrees. Any questions?
Wait, so if it's not regular, then when you do A plus B plus C plus D.
Yeah, if it's not regular, then we might need more information.
Plus blank equals 120?
Equals 720.
Yeah, that's what I meant.
Okay, yeah. Yeah, so you'd have to add them all individually together,
Yeah.
and then they would equal the sum of the interior angles. So you would need more information to determine individual angle measures. All right, let's see what we got here. Let's try this. Why don't you guys go ahead and find the measure of each interior angle if you know it's a regular nonagon. Nonagon means how many sides? 9. So tell me what the measure of each angle is inside a regular 9-sided figure. All right, so to find that answer, we need to know the sum of the interior angles of a 6-sided figure, or the IAS. So the IAS is going to be equal to n minus 2 times 180. So for a 9-sided figure, that's 9 minus 2 times 180, which is 7 times 180, which is 1260. So now if you take that 1260 and divide it by n, or if you use the IAS divided by n, then you're going to get 1260 divided by 9, and that's going to tell you how much each angle is. And I got 140 degrees. So hopefully you're seeing a pattern here. Triangles, regular triangles have angles that are 60. Regular quadrilaterals have angles that are 90. Regular pentagons were 108. Regular hexagons were 120. Regular nonagons were 140. The bigger the number of sides, the bigger the what? the bigger each angle measures. And that makes sense because the interior sum gets bigger and bigger too. Now, if we didn't have a regular figure, but we had some other information, we could find out missing angles just like we do in triangles. So here we've got a pentagon, and we know that 4 of the angles are something. So the measure of angle Y plus 90 plus 110 plus 120 plus 150 equals the IAS for a pentagon. And the IAS for a pentagon, in this case, is going to be 5 minus 2 times 180. Because that's the sum of the interior angles, is that formula right there. So the measurement of angle Y plus 90 plus 110 is 200, 320, 470 is going to equal 3 times 180, which is 540. And then we just subtract off 470 from both sides, and we get 70. So I can find the missing angle just by knowing enough information that I only have one variable in my equation. Is everybody okay with that? All right. Fun fact, and I don't know if you guys will think this is fun or not, but this is true. When you're dealing with the outsides or the exterior angles of polygons, if you add up all of the exterior angles, you will always get 360 as an answer. Always. So that might not make sense because there's more exterior angles on a 4-sided figure than there is on a 3-sided figure. But remember, the exterior angles are computed by taking supplementary values of each interior angle. And if the interior angles are small, their supplements are bigger. And if the interior angles are bigger, their supplements are smaller. So even though there are more exterior angles on the outside of a figure that has more sides, they're smaller in value. For example, if we had a 100 and we knew it was regular, its interior angle would equal 100 minus 2 times 180 divided by 100. So that would actually come out to be 176.4 degrees. The supplement to 176.4 is equal to 3.6 because 3.6 and 176.4 equal 180. So there's 100 angles on the outside of a regular 100 gon that measure 3.6. What's 3.6 times 100? 360. So 360 degrees, it has to be the answer when you're dealing with the sum of the exterior angles of any polygon. Doesn't have to be regular. How is that useful? Well, now we can find the exterior angle measure. What's the measure of angle 1 in the regular octagon to the right? Well, since all the angles are the same, they could share the same variable. And so 8x is going to equal 360. So x is going to equal 360 divided by 8, which turns out to be 45 degrees. So if I know that all the angles are the same, and I know that the sum of the exterior angles is 360 divided by those number of angles, I could find the exterior angle. How would I go about finding the interior angle? Well, you've got two choices at this point. You can use the formula, and the formula is, in this case, 8 minus 2 times 180 divided by 8, which would be 6 times 180, 1080. divided by 8, which is 135. And that would give you each interior angle. But then that's also going to be supplementary to the 45 that you already know. So for me to find the interior angles of a regular figure, it's easier to find the measure of the exterior angle and then subtract that from 180. Then I don't have to do as much of that. You do it however you want to. You can use the formula and plug it out if you want to, or you can use relationships between angles if you want to. That's completely up to you. All right. We've covered a lot of different stuff, so now let's see if we know the geometry to some of the stuff we've talked about today. What I'm going to do is, instead of finding the answer, I'm going to ask you to write down the formula. What would be the formula that you would use to find the sum of the interior angle measures of an 11-gon? And you can go ahead and plug the 11 in for n, but just write the first step. Just write the formula. How would you go about figuring that out? Do you know what that question is asking you? All right, so hopefully you knew that to use the formula, n minus 2 times 180. In this case, what we would do is we would take 11 minus 2 times 180, and that's what's going to give me the sum of the interior angle measures of the 11-gon. That's the IS. Okay? Next question. How do we go about finding the measure of the exterior angles of a 15-gon? All right, if you took the time to do any kind of math figuring on this problem, you missed something. Because what's the sum of the exterior angles of any polygon?
360.
So the answer to this one is just a straight up 360. There's no figuring to do. We just already know what it is. So you got to know when you got to do some figuring, and you got to know when you not got to do some figuring. What about find the measure of an interior angle and an exterior angle of a regular decagon? So a decagon has how many sides? All right, so you need to go through and tell me what the exterior angle and the interior angles are going to measure of a regular of that type of figure. All right, there were several different ways you could have gone with this problem. I think the way that I think is the easiest and I would have chose is I would have started out with the exterior angle. So the exterior angles are going to equal 360, the sum of all the exterior angles, divided by 10, and that's 36 degrees. And then I think I would have taken the interior angle is going to equal 180 minus 36 degrees. So 180 minus 36 is 144. And that would have answered the problem. Did anybody do anything different? What'd you do?
For the interior angles, I just put 10 minus 2 times 180 over 10.
So you did the formula to find the interior angle. So that was 8 times 180 divided by 10, and that still should have given you 144, right? And then what'd you do?
For the exterior angles, I knew that the sum is 360, and I just divided it by 10.
So for exterior, you used the same formula I did. 360 divided by 10 equal 36. A way to check is to add those two together and see if it equals 180, because these have to be supplementary to each other. If you think about it, you're talking about the inside of a figure here, and if this is 144 degrees, then this needs to be 36 degrees because they make a straight line. That's how exterior angles are formed. All right, good job. Tonight's homework, page 356, 7 through 25 odd, 29 through 35 all or odd, and 41 all.